two corridors, so corridor 1 and corridor 2 meet at right angles, and so I should draw the right angles. Two corridors meet at right angles and are 2 meters and 3 meters wide, respectively. Theta is the angle marked on the given figure. Theta's here. AB is a thin metal tube which must be kept horizontal and cannot be bent as it moves around the corner from one corridor to the other. So it says show that the length AB, so the length of the whole tube, or potentially the length from A to B, is in like a maximum, like a diagonal between corridors. Show that the length AB is given by L equals 3 over cos theta plus 2 over sine theta. So basically we need to find an expression for AB. So you can see this, we're aiming at 3 over cos theta plus 2 over sine theta. That's 2 parts basically. It's going to come from, say, you might call this bit kind of D1 and this bit D2 if we kind of split the thing up like that. And then presumably one of them's going to be 3 over cos theta, the other one's going to be 2 over sine theta, otherwise it's not going to be very good. So if you look at this, we're told that the corridors meet at right angles, which means kind of that this line must be parallel to this line if this is 90 degrees and so on, which is very handy. So I'm going to go ahead and draw a line like that and a line like that. This line is parallel to this line here, that makes a right angle, and this line is parallel to this line, and this line also makes a right angle. Very handy. Right, and you can see this line is 2 meters long, this line is 3 meters long, and also another rule, because these two lines here are parallel, you've got one line crossing the same thing. In fact, this line is parallel as well. By corresponding angles, this angle in here must also be theta. These pens are too thick, so you've got the theta, theta. So now if you consider the two triangles, the triangle 1 and triangle 2, we should be able to get an expression for D1 and D2. I'm just going to draw them here because it's a bit messy with a big pen nib. So triangle 1 kind of looks like this. Draw it big. You've got theta here. You've got your D1, 3 meters. So we want to find D1. So if you know you're at Sokotoa, well, that's H, that's O, and that's A. The two involved are A and H, which means cos K, which means cos theta equals A3 over D1. So a simple enough rearrangement of that says, move the D1 up there and the cos theta down there, so D1 equals 3 over cos theta. Looking good. Right, it's triangle 2, which is this one here. So we'll do the same again, so triangle 2. Looks like this, 2 meters, 2 meters, right angle there, a theta there, and a D2. So this time, HOA, ring ring, the D2 is involved in this, so it's O and H, which means sine theta equals 2 over D2, which means D2 equals 2 over sine theta. So you know your L, or sorry, the length of AB is D1 plus D2, so AB equals, so it's D1 plus D2, which is 3 over cos theta plus 2 over sine theta as required. L, which was AB, so L equals 3 over cos theta plus 2 over sine theta. I'm going to do them in different colours because I'm going to end up over here. So, want to find an expression for dl by d theta. It would be a lot more use if these were in index form, so equals 3 cos theta to the power minus 1 plus 2 sine theta to the power minus 1. something like that. Right, so we're interested in dl by d theta because we need to show when it equals 0. So dl by d theta equals, so if you're going to differentiate this blue term, it's a chain rule. We can do shortcut chain rule. So you're going to bring the power to the front, leave the 3, so equals 3 times power to the front minus 1 times the bit that's in the bracket, cos theta, drop the power by 1, minus 2, and then times by the derivative of the function in the bracket. The cos theta differentiates to minus sine theta. Okay, and then we're going to do the same for the red one, so plus, well, leave the 2 times, bring the power to the front, minus 1, times sine theta, drop the power by 1, minus 1 goes to minus 2, and then multiplied by the derivative of the thing in the bracket, sine theta differentiates to cos theta. Right, so now that's going to need quite a lot of tidying up. So minus 1 times 3 is minus 3. So, sorry, that's going to need quite a lot of tidying up. So you've got here a minus times a 3. So you've got 3 sine theta over cos squared theta. This is the blue term. Now this is 2 times minus 1, positive there, so it's going to be minus, and you've got cos theta over sine squared theta. Wait, I lost the 2. 2 cos theta over sine squared theta. So now you want to find a way to add these fractions. So what we're going to do is find a common denominator, which we're literally just going to do this kind of cross multiply butterfly method. So we're going to times these 2 together, and these 2, and these 2. So you're going to end up with equals 3 sine theta times sine squared theta. So that would be 3 sine cubed theta minus, then you've got 2 cos theta times cos squared theta. So that's minus 2 cos cubed theta, and then over sine squared theta cos squared theta. We're just multiplying the 2 together. We've been asked to show when dl by d theta equals 0, so it looks a lot more complicated than it is actually, because you've got this sort of fraction which is made up of a function of something on the top, function of theta on the top, divided by a function of theta on the bottom. Now this thing equals 0 when, just the same for any fraction really, when numerator equals 0, which makes things a lot easier. So we just literally have to solve 3 sine cubed theta minus 2 cos cubed theta equals 0, just like that. So this is actually quite friendly. All you need to do is get the cos cubed theta over there, so 3 sine cubed theta equals 2 cos cubed theta, like that. Then we're looking to get to tan. Remember the question says show that dl by d theta equals 0 when theta equals inverse tan the cube root of 2 over 3. So we're looking for a tan. The way we get a tan is with a sine over cos. So if we divide through by cos cubed theta here and divide through by 3, it's going to look like this. So sine cubed theta over cos cubed theta equals 2 over 3. So we're nearly in business. So you know sine over cos is tan, so sine cubed over cos cubed theta is tan cubed theta. So tan cubed theta equals 2 over 3. So that would mean tan theta equals the cube root of 2 over 3, which would mean that theta equals inverse tan of the cube root of 2 over 3 as required. We found the value of theta when dl by d theta, the rate of change of the length of the rod or tube with respect to theta, is 0. And we've been asked for part C to find the L when theta equals inverse tan of cube root of 2 over 3. So basically, oh, by the way, if you do inverse tan of the cube root of 2 over 3, so theta approximately equals 41.1 degrees, right? Just using a calculator. So when theta equals tan inverse tan of the cube root of 2/3, L equals, remember, L equals 3 over cos theta, so 3 over cos, and I'm going to write 41.1 in because I don't want to write this all the time, so 41.1, but you should certainly not, if this is in a paper, do not just write 41.1. You either need to use this, as in write the whole exact thing in, or even better, just use your ANS key. If you've just done this calculation to get that angle on a calculator, just use your ANS button. So you're going to write 3 over cos ANS plus 2 over sine ANS. Something like that. But I'm not going to write it here, but you should use your ANS. It wouldn't write it, but you'd use it. So when you put this into your calculator, it tells you that L equals around 7.02 meters to 3 significant figures. Okay, so at the moment, the question so far, we have found an expression for L in terms of theta, as in the length of the rod, or the length of that straight line in terms of theta. We've found that's when theta is around 41 point something degrees, 41.7 degrees. Dl by d theta is 0, so the rate of change of theta with respect to 0, So what we've found so far, we have managed to find an expression for L in terms of theta, and then we've differentiated L with respect to theta, L being the length of that straight line AB. And then we've found that dl by d theta, the rate of change of length with respect to theta, is 0 when theta is around 41, 42 degrees. There's an exact value there, but I'm not going to bother with that. We need to actually look at it contextually. It's another calculator question. So if we look at the graph of the derivative, it will probably tell us the actual nature of this. We know we found a stationary point, but we don't know what it is. So here, and it's quite a tricky one to put in, I'm using the TI here, but the dl by d theta was 3 sine cubed theta minus 2 cos cubed theta over cos squared theta sine squared theta. So remember that sine squared theta is sine theta all squared. When I say theta in a calculator, I mean x. So put it in, very, very careful, especially if you're using an old Casio, where that doesn't do fractions. It's not easy. But anyway, so you get an expression like that, and then you go to the graph, and what you should do is think about the window. So if you go back to the diagram, you do have a natural domain. So thinking that you've got this 90 degree, but theta can't possibly be more than 90 degrees. So if it was less than 0 or more than 90, it would be pointing in the wrong direction to actually go around the corridor. So it would either be pointing straight at one of the walls. So you've got this natural domain of x between 0 and 90, not inclusive, exclusive. So I'm put that in. As far as the y values, you just kind of experimenting with them. Remember, that's the dl by d theta, so it's not like you can think about length of rod and get a sensible value there. You just, if they don't look sensible, then go back to it and go back to the window and try again. Anyway, let's have a look at the graph. So there you go, from 0 to 90, we've got quite a nice graph here. So we're interested in this 0, which hopefully will be 41 point something. So second calc, find the 0, and you're going to go left of it and right of it, and then you're going to guess just somewhere close. And fortunately, At 41.1 degrees, we have a 0 in dl by d theta. So now, looking at that, it looks like it's negative on the left-hand side and positive on the right-hand side. We should just check with the trace function. So we're at 40. You can see that dl by d theta is negative as we go to the left-hand side of that 0, and it is positive as we go to the right-hand side. So now we'll interpret that in a sine diagram. Well, actually, just before we do that, if this graph doesn't look right, it would probably potentially be, if you're in radian mode, it would look very different in radian mode. So if you're working with degrees, make sure you're in degree mode, so the graph is just there. We can conclude that you've got this sine diagram of dA by dx, so you had this 0 at around 41.1 degrees, something like that. The dl by d theta, sorry, not dA by dx, dl by d theta was positive here and negative here, which means this is a minimum, right? So what it is, you're minimizing AB. So what you're doing, you're minimizing AB. So at the time when theta equals 41.1 degrees and the length equals 7.02 degrees, it's telling us that at 41.1 degrees, when you're at an angle of 41.1 degrees, so that length AB will be at its minimum. So that's the smallest length that you're going to have to negotiate when you move this, when you transport the rod. So basically, that corresponds to a length of 7.02 meters. So if your rod is anything bigger than anything longer than 7.02 meters, then it's not going to fit around there without bending, because you know that once it gets to 41.1 degrees, you reach the minimum length. If that angle is different, you'll be able to get a bigger rod in, but to be able to get around the whole corridor, then you're going to need something that's under 7.02 meters long.